Hey everyone, it's JP, and today I wanted to go over a video where we derive the FiO2 equation when using a nasal cannula. So as most of us know, the FiO2 is the fraction of inspired oxygen. And let's go over why this kind of topic was brought up, or I was sort of thinking about it. So a little bit of background. FiO2 is the fraction of inspired air comprised of oxygen, which is labeled O2, and atmospheric FiO2 is roughly around 21%. We can increase a patient's FiO2 by adding pure oxygen to what they breathe. And the reason why this is important is because it's actually a quite useful factor when interpreting arterial blood gas results, amongst other things. So, for instance, there's something called an AA gradient, which is a arterial alveolar gradient, or alveolar arterial gradient actually. And this can help interpret some pathologies in the lung. And so FiO2 is needed in order to have a meaningful result when using this metric. So what's the issue? Well, when a patient is intubated connected to a ventilator, we actually know exactly what the provided FiO2 is. In fact, it's displayed on the ventilator screen and it could be adjusted. But the problem is, what if the patient is actually just using a nasal cannula that we hook onto a wall with a certain O2 flow rate, like 1 liter per minute, 2 liter per minute, something like that? Well, figuring out this relationship is actually not that intuitive. And there are a lot of good approximations for estimating this, and quite a bit of information on the web on how to approximate it. A lot of people say somewhere between 3 to 4% per liter of O2 that you give, and this is actually pretty accurate, but I'm kind of going to go a little bit more in depth about the math behind this and show why this outcome is true. And so here is a little disclaimer. So let's go over the basics. If we have a volume, let's say a volume of gases in a cylinder that we call VT for volume total, or volume tidal if it's something that we're breathing. Now we can partition this into different gas components. So let's say one of the gases takes up volume A and another one takes up volume B. Now if the volume A gas was oxygen, and if the volume B was, let's say, remainder of air, which is mostly comprised of nitrogen, but can also have other trace gases like argon, CO2, things like that, then we can go ahead and actually calculate something called the fraction of oxygen amongst this entire volume. And this would simply be the volume that the O2 is taking up over the volume of the total container, not the volume of the remainder of air, but of the O2 plus the air. And in atmospheric conditions, I'm going to go ahead and call this F0, which is just the FiO2 in atmospheric air, and this is roughly 21%, or 0.21. So here's a little schematic of kind of what goes on when you hook a patient up to a nasal cannula. So you have a source of pure oxygen from the wall, and here the FiO2 in the actual, or really the F here in the pure oxygen is 1. It's all O2, so there's nothing else. So basically the entire volume is of this gas, the red one, versus the air around it is 0.21. So when a patient is breathing or inspiring, the V, which normally means volume, having an accent of a dot over it, means flow. And so this is the rate of the volume that's going in. When there's flow into the nose, then this is comprised some parts of the VO2, which is coming from the wall, and the remainder from the V air, which is not provided by the nasal cannula. And so we know that some of the air, or some of the gases that are going in, are going to have a pure a fraction of 1, and then others are going to have 0.21. And the biggest assumption of this entire kind of like model is that it's of a closed system, meaning that everything that's hooked up to the patient while he or she is inspiring is intact. So there's no like leakage to the outside surroundings of like O2 coming out here, things like that. So we're assuming everything that we're providing during inspiration is taken up by the patient. So let's go over what a respiratory cycle is briefly. If we graph time versus volume, or actually volume versus time, we know that people, humans, tend to breathe according to this sort of relationship where we inspire, the volume goes up to a certain point, which is kind of like the tidal volume, and then we expire, and then the volume goes down, down to sort of like a residual volume, and then the cycle repeats. So we can define this symbol RR as the respiratory rate, and this is just the number of cycles in 1 minute. So here we'll focus on just one of these cycles of the many, and we'll break it down into the inspiratory part and the expiratory part. And basically, I'm considering expiration to be everything that's not inspiration. So let's say, someone actually breathes out and then there's a little bit of a gap before they breathe in again. That's fine. We'll just still call that part of expiration. So here, this chi or x basically means the fraction of, and so the fraction of time that they're in, or the fraction of the cycle that they're in inspiration is xi, and the fraction of the cycle that they're in expiration is xe, and these must sum up to 1. So usually people are like 1/3 in inspiration and then 2/3 in expiration, and so this number would be like 0.33 and this number would be like 0.67. And then we know that the time of one cycle, time of one respiration cycle, is just 1 over the respiratory rate. So if someone's breathing, let's say, 20 times per minute, then one cycle is going to be 1 over 20, and it's going to be 0.05 of a minute, which makes sense. Alright, so time to hit up the derivation. This is going to look complicated, but it's actually not that bad if you kind of, I'll try to walk you through it and hopefully get to the end where it all makes sense. So I'm always going to be using I, the subscript I, for inspiration. So big T is time, and this is the time that someone is in inspiration. And so this is simply the time that they're in one respiratory cycle, and then, times the amount of time that they're in inspiration in that cycle. So it's basically this times this portion here. And so this is the, basically what I'm trying to find out, this time right here. And this would be the time of the total cycle times the fraction that they're in inspiration, or xi. And so we know that TR is just 1 over RR, and so we get this. Now next I want to take a look at the volume and flow relationship. So if we have the flow during inspiration, well, we know that the average flow is just going to be the volume total that they inspire over the time that it takes for them to inspire. And so we can rearrange this and get that the volume total that they inspire is the flow rate times the time that they're actually inspiring. And here we can go ahead and expand this, and we know that we solve for Ti up here, which is xi over rr, and so it's just substituting that in, we get this relationship. And I'm going to go ahead and store these two up in this box in the top right hand corner because we'll be using them down the road. Alright, so we'll go ahead and import the first one, and we know that the total volume that we inspire is, again, the flow rate times the time that we're in inspiration. Now, let's take a look at the flow rate of inspiration. And we know from before, from our diagram, that the total flow rate that we inspire is going to be comprised of two components. The part that's coming from the O2, from the wall, and then the remainder, which is just going to be coming from the surrounding air. So VI dot is going to be VO2 dot, which is coming from the wall, and then the remainder is going to be picked up from the air. And again, we're assuming a closed system. And then Ti carries forward. So here I'm going to put this in blue because it's going to be something that we want to use later. But here I'm keeping the VO2. And then, funny enough, I'm actually breaking down the V air back to VI minus VO2. So the flow total minus whatever we get from the O2 is going to be the remainder, which is from air. So I'm kind of rewriting it, I'm kind of reversing it again, even though we know that VI is VO2 plus V air. I'm writing V air as VI minus VO2 because it'll make the math work out better. And we carry the Ti. So now we want to look at the portion of this that actually carries O2 in. So how much volume of O2 do we get? Well, this is going to be depending on what we inspire, the flows of the things that we inspire, and how much each of those carries oxygen as part of them. So we know that the O2 coming from the wall is going to carry 100% oxygen. And so this component of the V total, this flow, is going to be carrying 100% oxygen, So whatever this is going to give us its full component of oxygen. And then the air, or the remainder of what we pick up, is going to be carrying F0, which is roughly 21%. And so this times the time that we're in inspiration, because flow times time is the volume, will give us the volume of O2 that the patient breathes in. And so remember, what we're looking for is the fraction of O2, so we want to know the volume of O2 over the volume total that they breathe in, because that will give us how much O2 is taken in. So let's go ahead and put this red formula up top and then this blue formula down here. And then, so here I'm just rewriting them. And then here I'm just canceling out the TIs, because we can see that the TI is common to both the numerator and denominator. And if we go ahead and distribute this F0 here and here, and then we go ahead and divide the numerator, each numerator component by VI, or the flow of I, then we get this, that F is equal to the flow of oxygen over the total flow of inspiration plus F0 minus this same factor times F0 here. So let's just bring this and copy it to the next page. So this is what we had before. And now let's take this F0 and move it over to the left hand side. So we get F minus F0, and then we keep what's remainder on the right hand side. And now on the right hand side, we notice that these two are the same, so let's just factor this out. So we'll get the flow of O2 over the flow of total inspiration, and we'll get 1 minus F0 on the right hand side. So I want to call this thing on the left delta F, and this is basically the new FiO2, or kind of like where we attain, minus the atmospheric FiO2. So it's the change in the fraction of inspiration oxygen. And calling this left-hand side delta F, we just get this formula, putting 1 minus F0 here, and then again, the flow of inspirations on the bottom, and then the flow of O2 is up top on the numerator. I'm just putting it out here to the side. And so now I want to take this thing that we've been carrying forward from up top and put it and substitute that for the flow of inspiration. So finally we get what's boxed in, which is that delta F is equal to 1 minus F naught up here, times the fraction of time that we're in inspiration, and then divided by the total volume that we breathe in on average, times our respiratory rate, times the flow of oxygen. And that makes sense because here the flow of I is on the denominator, and so these two things get placed here in the denominator, while what's on the bottom here gets flipped up to the top. So this is it. This is our final formula. And here is what each of these symbols represents. So again, delta F is the change, and I want to kind of just make sure that that's understood, in FiO2 from atmospheric F naught. So let's say, you know, something up here, like let's say there's no oxygen coming in from the wall. Okay, so let's say this is 0. Now delta F is 0. Does that mean that patients breathing in 0 oxygen? No, it means that they're getting all their oxygen from air, and so delta F is 0, and so what they're actually breathing in is just F naught. There is no change from F naught because the change is 0, but they are definitely still getting oxygen from the air. So this 1 minus F naught is just a constant. It's 1 minus 0.21, so that's around 0.79. Again, Xi is a fraction of time in inspiration, usually about a third for most people. VT is the tidal volume that the patient breathes in during their inspiratory portion of the cycle. RR is the respiratory rate per minute. And then flow of O2 is the cannula flow of pure O2 liters per minute coming in from the wall. So this is actually the final formula, and that's how we derive it logically. So in the last slide, I kind of just want to touch on why it makes sense to not, you know, always bust this out in clinic or something when you need it, but to have like a general approximation in mind, and why it's good to use the 3 to 4% rule that other people often mention. So let's just go ahead and use this formula, but plug in some average values. So again, most people have about 1/3 of their cycle in inspiration, 2/3 in expiration. So we can plug in 0.33 for that. The average tidal volume of an average person is around half a liter. And then usually the respiratory rate of a patient at rest is around like 14 cycles per minute. So this is the same formula as above, and let's go ahead and plug in these numbers. Remember, 1 minus F naught is just a constant, it's 0.79. times 1/3, which is xi, and then divided by 0.5 times 14, which are on the denominator. And we'll leave this as a variable. And so once we kind of grind out all these numbers, we get 0.037 times the flow of O2. And so we know, remember, that this is the change in F, not the actual final FiO2. So an average change in FiO2 is roughly 0.037, which is 3.7% times the flow of O2. And so this is kind of how you end up getting that approximation of around 4% per liter that you give the patient from the wall. So this flow of O2 is literally just what you dictate in the nasal cannula. So let's say, I put this at like 2 liters per minute or 4 liters per minute, then each liter will roughly be scaled by a factor of about 4%. So if this is 2, I'll be bumping up the FiO2 of the patient by roughly 8%. If this is 4, it might be something on the order of 16%. A little bit less, but so this is how we get this number. And it sort of does make sense to just keep the general form of this formula in mind, because you can't say that this holds true universally, this approximation. This holds true on average, but let's say someone really does not like breathing, right? So let's say their xi is 0, all they do is expire. Then this is going to be 0. You're not going to give that person any increase in FiO2, no matter how much you're pumping from the wall. Let's say 8 liters or something. You're really just not going to increase their FiO2 at all. So it's sort of, it makes sense to kind of have this general frame in mind, even though you're ultimately probably going to resort to the approximation. But just wanted to show you how you end up getting here. So hopefully this was helpful. And remember, this is just, a model that, although we derive from basic principles, still relies on assumptions that not all patients might adhere to. So yeah, thanks for watching.